see the slides. Great. So I think we can get started. So this talk is on kind of interaction data and studying the identifiability of such interaction data across time. And so Ana-Maria, thanks a lot, and the floor is yours.
Yes, thank you. Can everyone see my screen and the slides changing? Yes, okay, thank you. Hi, everyone. My name is Ana-Maria, and I'm a PhD candidate at Imperial College London. The work I'm presenting today is the product of a collaboration with Federico Monti, Stefano Marone, Xiao Wendong, Michael Bernstein, and Yves-Alexandre Monjoie. At the time when I'm giving this talk, my work is awaiting publication in a journal, so I would like to kindly ask you, if possible, to not share it on social media yet. My work is about the identifiability of interaction data. And for the context, today our interactions are increasingly mediated by technology. We use our mobile phones and smartphones to communicate with family and friends. During the pandemic, we have been using video conferences for work, and even our offline interactions could be tracked by contact tracing apps exchanging signals when we are in proximity to other people. Data about our interactions are collected on a large scale for business and research purposes. By interaction data or metadata, I mean a record or a log consisting of pseudonyms of parties, timestamp, and possibly other information. For instance, mobile phone interaction data can be used to estimate population density at specific times and locations, and have also been used to forecast the spread of epidemics. But interaction data can be very sensitive. They are very granular. They can reveal who we talk to, who we meet, when, and for how long. The Snowden revelations a few years ago have drawn the public's attention to the bulk collection of mobile phone metadata. And even though metadata does not contain the content of an interaction, for instance, a recording, privacy advocates have long argued that, and I quote, metadata are data. For all these reasons, the release of interaction data or its sharing can be problematic if the data can be linked back to people. The study of reidentification attacks allows us to quantify the risk of linkability of data sets. Reidentification attacks use auxiliary information about people to identify them in another data set. And a lot of work exists applied to different types of data, falling into what I will be calling from now on matching attacks. Matching attacks assume that an attacker would have access to auxiliary information about a user that's exact or time stable, such as a zip code or friendship in a graph. When it comes to interaction data, we argue that profiling attacks are more meaningful to study. The goal of what we call a profiling attack is to re-identify the user in a data set that was collected in a disjoint time period compared to the auxiliary information available to the attacker. And in this work, we propose a profiling attack model for interaction data. It is useful from now on to switch from the tabular representation of interaction data as a collection of logs to a graph representation. So starting from the data set, we construct the graph of interactions where the nodes are the users, and there is one edge for every interaction. And we represent the behavior of a user here in yellow via its k-hop interaction graph, which consists of the neighbors of the node, so the contacts of the node, the contacts of the contacts, and so on, up to k-hops. And what I show on the right is what we will be calling from now on the k-hop individual interaction graph from a specific time period. We assume that an attacker would have access to a data set of KIAGs or k-hop individual interaction graphs from n people. This is what is shown on the left, and another KIAG from a user Alice. And the main assumption here is that the data set and the auxiliary information come from disjoint time period. And the attacker's goal is to find Alice in the dataset. So we develop an attack using deep learning for identification, consisting mainly of 3 steps. In a first step, we create a set of features for a user based on the interactions in their K-hop individual interaction graphs. The features summarize the interactions of the node and are computed using the Bandicoot API. This is a tool originally developed for mobile phone interactions to compute features that summarize the interactions. Then in a second step, we use graph attention networks for embedding a graph representation of the KIG. And in a third step, we optimize the weights used to compute these the embeddings using the triplet loss. More specifically, we construct embeddings from users' weekly interaction graphs, and the triplet loss aims to bring embeddings of the same user but different time periods closer to each other compared to embeddings of different users. We validate this attack using 2 case studies. The first one, in the first case study, we use a data set of more than 40,000 people from a mobile phone carrier. And the figure shown here illustrates our evaluation setup. Namely, it is useful to think of the data set along 2 dimensions, the temporal dimension and the users. And we assume that the data set available to the attacker consists of the first 15 weeks of data. The remaining weeks are used to draw auxiliary information. Every week of data contains the 3 interaction graphs from all the people that we study. Out of the data set of 15 weeks, we assume that the attacker would use the first 14 weeks to train and validate the machine learning model, while the last week in the data set is what we call the reference week. So to carry out the attack, the attacker would embed data from the target user in one of the auxiliary weeks and compare this embedding to the embeddings of everyone in the reference week. The main result here, so we assume that the reference and the target weeks are consecutive. So there is only 1 week of delay between the reference and target data. And we computed the fraction of users who are correctly identified within rank R. To do this, we retrieve the top R matches. And if the correct match is among the top R candidates, we declare the attack a success. And our results show that the approach we propose correctly identifies people almost 15% of the time using only 1 hop interactions, and more than 50% of the time, so more than half the time, when using 2 hop interactions. As we increase K, so 1 hop, 2 hop, 3 hop, the number of hops contained in the individual interaction graph, the probability of identification increases, but with decreasing returns. We believe that this is probably because the information about faraway contacts could be less important for identification, at least using this model. And as we increase the rank R, so for instance, identification within rank 10, the numbers only go higher. Next, we vary the time delay between the data set and the auxiliary information. We found that the probability of identification computed using our model decreases slowly as the time delay increases. And even after 20 weeks, using 2 hop interactions, for instance, so it is this point here, our approach identifies people 24% of the time. We also found a sharper decrease for some of the weeks shown in the vertical gray lines. So when the auxiliary information comes from these weeks, In a post hoc analysis, we found that these weeks correspond to national holidays, suggesting that it is possible for outside events to maybe influence the behavior of people. The next question we ask is, what happens if the attacker has access to more weeks of auxiliary information? So far, we only assume that the attacker will have access to 1 week of data. So we start from the week consecutive to the reference week, and we add more weeks in the future up to L weeks. We found that the probability of identification increases sharply at first as more data is available, and then plateaus. Roughly after 16 weeks, it even starts to slowly decrease, probably due to the fact that data from distant weeks could be less useful for identification. In the attack considered so far, which is scenario A on this figure, the identities that we test on, that we study whether they can be identified, are also used to test the model. Only the training and test periods are disjoint. So data is indeed unseen because it comes from a different time period, but the identities are the same. So we carry out an experiment to study whether our approach generalizes to other identities. So we design a controlled setup. In B, for instance, the testing identities in yellow are also seen during training. In C, the testing identities are new, but data from that time period from other people is seen during training, while in D, both the testing identities and the time periods are unseen during the training. And results shown here on the left show that the performance is similar across scenarios for all values of K. The numbers are slightly different. So for K equals 1, there's a higher probability of identification compared to the previous results, because the number of identities is smaller here. Like to be able to run this analysis, we reduced the size of the set. And so far, I've discussed the impact of several factors on the probability of identification. There are a few others that we looked at, for instance, the population size and whether the results would change if we trained on future data and tested on data from the past. I refer you to our paper, hoping that it will be soon published. Finally, we carried out a second case study where we looked at interaction data from a Bluetooth close proximity network. So this is a data set that was collected over 4 weeks from students on a university campus. So people who have data across the 4 weeks, they are almost 600 people. And the interaction data contains the pseudonyms of the parties, a timestamp, and another field which is a proxy for the distance between the Bluetooth devices. And we ran a similar attack to what I presented before, using weekly data. The first 2 weeks are used for training, the second and the third for validation, and the last one for testing. We found that more than 26% of people could be identified using one-hop interaction contacts. However, I would like to caution that we don't believe our results to apply to robust privacy-preserving contact tracing protocols such as Google and Apple's exposure notification, which have been used in the context of the recent pandemic. To conclude, in this work, we propose a general profiling attack for interaction data, and our results on 2 real-world data sets suggest that these attacks pose a risk to people's privacy. They also emphasize the need to consider these attacks when assessing whether data sets or protocols are anonymous. Finally, we believe our results to show that RIP pseudonymization across time might not be effective in protecting interaction data. By RIP pseudonymization across time, I mean, for instance, changing the pseudonyms in an interaction data set after 2 or 3 or 4 weeks. So since in this analysis we use weekly information, we believe that our results suggest that 1 week, RIP pseudonymizing after, let's say, 2 weeks or 3 weeks might not be effective because the data sets could be linked. I would like to thank you for your attention, and if you have questions.
Thanks a lot, Ana-Maria, for the nice talk. So we have now a few minutes for questions. So there is one by Olia in the chat, so who is asking, what do you think could be defenses against such attacks?
This is a very good question. Well, I think probably the best security measure would be to restrict the access to such data to only allow access for a specific use case. As I said, RIP pseudonymization using long periods of time is probably not effective. So maybe using more frequent RIP pseudonymization, like 1 day or 2 days, possibly adding noise, but I think it very much depends on the use case, because adding too much noise could destroy the utility of the data. But I mean, it depends on how fine-grained this data is. I think our results show that the data is very identifiable. So yes, I think depending on the use case, aggregating it, applying differential privacy.
All right, thanks. There is another question by Adria. Could you comment more on why re-anonymizing after X weeks does not help? This was not there in the original model you presented, right?
Re-anonymizing after X weeks. Oh, yes. Because we assume that the data, so we do not use that the pseudonyms in the data set and in the auxiliary informations would be consistent. So we train a model on a data set where the pseudonyms are consistent across the training data set, but the pseudonym in the K-hop interaction graph available to the attacker is supposed to be different. And actually, to train the machine learning model, we only need the pseudonyms of the original node, so of the central node at the center of the KIG. We only need that pseudonym to be consistent across weeks, because the graph attention network is invariant to the order of nodes. So what we show is that data sets from different time periods can be linked together. I mean, we can at least link one identity from the target week to the identity in the past week in the data set. Sorry.
Okay, thanks. Maybe I have also one, so it's more maybe a little bit about the model you used for the attack, which is in the end not a straightforward model, right? It's like multi-layer kind of graph network. So I was wondering a bit whether you considered maybe simpler baselines for comparison. For instance, one could maybe generate kind of simple spectral features about the graphs, and it's I guess it's kind of interesting also to know a bit more about what kind of information is useful or needed to do this re-identification. Is it really something complex about the graph structure, or maybe some more kind of direct feature computed on the graph could be enough? So I don't know if you have looked into this a bit, or whether you can interpret also the model you proposed to understand this.
Yes. So first of all, when we use k equal 1, actually we just use the Bandicoot features for the matching. And here we obtain 15% re-identification rate. We compared ourselves with another baseline from the literature. This is a prior attack on mobile call graphs. The setup is slightly different because they do node pair classification as opposed to re-identification. And their approach uses random forest, and the features of the graph are histograms of degrees of neighbors. So we found that the neural network, like our whole approach with a neural network and triplet loss, performs much better, both in their node pair classification setup and in the re-identification setup. We also studied other baselines where we use hand-engineered features based on the K-hop interaction graphs, and in all of the cases, it helps performance. Other than that, we looked at different features, what happens when we remove them. This is not a result that is reported in the paper, but removing one single feature doesn't change very much the result. It's basically all of them.
Okay,
yes,
thanks.
but
I guess having some insights about what makes the data re-identifiable could also maybe help designing defenses to kind of follow up on all Jasker's question. But thanks a lot.